Integrated 2, Lesson 111. Really is about working in groups and just sort of understanding things about shape and how Venn diagrams work. So I typically skip problem 1-1 and problem 1-2. I don't really assign group roles. I expect you guys to work in groups, but not necessarily, with defined roles. So what we have here is these Venn diagrams, and I hope you guys are comfortable with the Venn diagram, but essentially if we use this as an example here, so it has at least one pair of parallel sides, that's our first condition, and has at least two sides of equal length as our second condition. Well, what happens when only the first condition is true but the second condition is false? Well, we put it in spot A, right, over here. And if both conditions are true, we'd put it in the middle or that overlap into spot B. If only condition 2 was true but condition 1 wasn't, we would put it in spot C. And if neither condition was true, we just sort of leave it on the outside and we put it in spot D. So let's go ahead and get started with there. We're going to categorize these shapes in this list over here with it into has at least one pair of parallel sides as condition 1, has at least two sides of equal length as condition 2. So starting with the square, a square, both those conditions are going to be true, so we would put that in the middle. I have a suspicion that my middle is going to fill up on this one, so I'm going to try and put that out of the way, but it has opposite sides parallel and all the sides lengths are the same. A kite, well, a kite doesn't have parallel sides, but we do have two sets of sides that are the same length. So I will go ahead and grab that one and put it over into this side where we have the equal length but not parallel sides. A rhombus is like a squish square, so these opposite sides are parallel and all the sides are the same length. So again, I will put that in the middle. A parallelogram is like a squished rectangle, so again, the opposite sides are parallel and these sides are the same length and these sides are the same length. So I will go ahead and put that one in the middle as well. A trapezoid. There's many different kinds of trapezoids. However, just a generic random trapezoid would be like this one, where the side lengths aren't the same, but we do have opposite sides parallel, so I would go ahead and put that over on the left side. A rectangle, obviously the opposite sides are parallel, and we have a couple of sets of equal length sides, so I'll put that in the middle. A quadrilateral just means four sides, so nothing special about this, no parallel sides, no equal side lengths, so that's my spot D, just sort of up and out of the side. And in the book it says it on the bottom, but obviously I have all the stuff in the way already. All right, an acute isosceles triangle. So an acute isosceles triangle would look like this, where two sides are the same length, but we have no parallel sides. So I'm going to go ahead and put that on the right. An equilateral triangle means all the sides are the same length, again, but no parallel sides. So I'll put that on the right side as well. An isosceles trapezoid. An isosceles trapezoid, opposite sides are parallel, and these two legs are equal, so I'll put that in the middle. A scalene right triangle. A scalene right triangle is a right angle where all side lengths are different, so that's not going to have parallel sides or equal side lengths. An obtuse scalene triangle, again, an obtuse scalene triangle means all the sides are all the sides are different sizes, so obviously, and there's no parallel sides in a triangle, so it can't be that. An isosceles right triangle, so these two sides would be the same, so I'm going to go ahead and put it over here on the equal side length. A hexagon, opposite sides are parallel and all the side lengths are the same, so I'll put that in the middle. A pentagon, all the side lengths are the same, but there's no parallel sides, so I'll put that on the left. Oh, I think on the right, my mistake. No parallel sides, but all the side lengths are the same. And finally, a right trapezoid. The side lengths aren't the same, but they are parallel, so that will go over to the left. So when I categorize those shapes, it would look something like that. If we go to problem B. Problem B has only three sides and has a right angle. All right, so let's go ahead and see what that would look like. So square has a right angle, but it isn't three sides. A kite is neither, right? A rhombus is neither. A parallelogram is neither. A trapezoid. Again, a regular trapezoid is this one here. I got neither for that one as well. A rectangle, we definitely have some right angles, so we'll put that on the right side. A quadrilateral, obviously, is neither. An acute isosceles triangle. So now we're finding some triangles, right? Acute isosceles triangle. We're going to go ahead and put that on the left side. It has 3 sides. Equilateral triangle, again, is going on the left side. No right angles there. An isosceles trapezoid. That's going to be neither. And a scalene right triangle. Well, there we go. It has 3 sides and it has a right angle. An obtuse scalene triangle. We have no right angles, but we do have 3 sides. An isosceles right triangle, obviously it's going to go in the middle. It has 3 sides and a right angle. A hexagon is neither. A pentagon is neither. And a right trapezoid is, actually a right trapezoid is going to have a right angle. So we'll put that there. So that's what it would look like if we categorize those shapes with those 2 categories. And finally, the last one that we're going to do here is how would we categorize has reflection symmetry and has rotation symmetry. So for that, hopefully we remember this from Integrated 1, where reflection symmetry meant it was almost like a mirror, or if you cut it in half down the middle, it could overlap on each other. And rotation symmetry meant that if you picked it up and literally spun it, that it would look the same. And remember, there's no such thing as 360-degree rotation symmetry. So again, rotation symmetry, 180-degree rotation symmetry means you pick it up, turn it 180 degrees, put it back down, would it look the same? Reflection symmetry means if you drew a mirror down the middle, would it look the same? So a square, yeah, that would be for both, right? If I picked this up and turned it 180 degrees, it would look the same. And if I went ahead and put a line down the middle, it would look the same. A kite, it definitely has reflection symmetry, but I do not believe it has rotation symmetry. So we'll go over here. A rhombus looks like it has both, right? We can cut it in half or we can spin it. A parallelogram looks like it has rotation. I think it does actually have reflection at that diagonal angle right there, right? So I would say both, although the book might disagree with me. I do think there's reflection symmetry right there, and definitely rotation symmetry. All right, a trapezoid. A trapezoid really should have neither, just a regular trapezoid, neither. A rectangle should have both, but down the middle you can spin that or cut it in half and it would look the same. A quadrilateral is going to have neither. There's nothing special about a quadrilateral. An acute isosceles triangle, well, if I cut that thing in half, it would definitely look the same, but if I turn it upside down, it wouldn't. So I would say it has reflection symmetry. An equilateral triangle for sure can cut it in half, but again, if you did 180, it would be upside down. So I'll just say reflection symmetry. Isosceles trapezoid, if I cut it in half, it would look the same, but if I turn it upside down, the shorter side would be on bottom, so we'll say it has reflection symmetry. A scalene right triangle, nothing special about a scalene right triangle. It's not going to be able to get cut in half or anything to look the same. An obtuse scalene triangle, again, I can't turn it upside down and I can't spin it. An isosceles right triangle, it looks like if I cut it in half right there, it would look the same, but if I spun it around, it wouldn't, so I'll say reflection symmetry. A hexagon definitely has rotation, and definitely if I cut it in half, looks the same, so I'll put that in the middle. A pentagon definitely has reflection, but the rotation, that point would be on bottom, so I'll say no. And then finally, this one's clearly no for both. So there we go. We have a lesson on not only these shapes and hopefully remembering what these shapes are and just some things about those shapes, but also how to use these Venn diagrams.